In this video, I am going to cover logistic regression. Now, logistic regression really is the go-to machine learning algorithms when we are working with binary class. I am going to use logistic regression to illustrate how you actually implement classification-based machine learning. Now, I use logistic regression because it has very similar form to linear regression. It's easier to grasp the concepts, so that's why I decided to use logistic regression to illustrate these concepts. I mentioned prior that logistic regression is the go-to linear classification algorithm for two-class problems. What is two-class problems? These are the binary, yes or no, 0 or 1. It is very easy to implement. The other beauty of logistic regression is that it is easy to understand, and also you can actually get pretty good results on wide variety of problems, even though the expectation is that the method of your data is violated. So I'm just going to provide a little bit of the so-called description of logistic regression and how is it derived and where is it from. Now, logistic regression is named because of the function used at the core of the so-called method, which is the logistic function. I provided a link here for you to actually look it up under Wikipedia. You can see that it is a S-shape or sigmoid curve with this equation as the representation of it. Now, the so-called statistician or the from the biological or biology field, they use this sigmoid function to study with relation to population growth. Now, the idea here is that the initial stage of growth is approximately exponential. Then once the saturation kicks in, the growth slows down, and then at maturity, the actual growth stops. So there's a wide range of application of logistic function, definitely ANN. If later on, if you are gonna learn about deep learning, logistic regression is used widely. Biology, in particular ecology, study of bacterial growth, on and on it goes. So let's come back here. So so we mentioned about sigmoid function was developed by statisticians to study the properties of population growth in ecology, and already cover rising quickly, maxing out, and reaching the capacity of the environment. It's basically S-shaped, and it can take any real value number and map it into a range of 0 and 1, but it never reaches the exact limit itself. So this is the actual mathematical representation of the sigmoid functions. 1 over 1 plus e to the power of minus x. E is the base of the natural log, and x is the value that you want to transform via the logistic function. Now, just to give you an intuitive feel of this function, I'm gonna just use this to actually show you, write some codes so that you actually can get some feel of it. The first thing is that we're gonna import some basic functions or libraries. We need NumPy. I'm just gonna use matplotlib for visualization, and I'm just gonna draw it in line as well. So I'm gonna plot between the range of minus 10 and 10 plus 10 with 10 segment that to 1000 segments, and you can see that this is really the representation of the sigmoid function. So let me just label it here, and that's the title of it. So as we plot this, you can see the classic sigmoid function. The initial period, you can see the exponential growth, and then once it matures, it saturates and it taper out. That's exactly this figure here. We can probably look at the range of minus 6 to 6 rather than such a big range, but for easier visualization, as you can see, we can actually plot that via this way. So this is for you to actually get a feel of it. You can play with it a little later. Okay, so the logistic regression function, as I mentioned before, has a very similar representation like linear regression. Now there's a slight difference in that the output value being modeled is in probability between 0 and 1. You can actually switch it to become binary in nature. I will illustrate that in future video when we are actually covering classification. Okay, example. So this is what it looks like, the logistic regression equation. Earlier what we show is the sigmoid function. You notice that there is the x, 1 plus, earlier what we have here is 1 divided by 1 plus e to the power minus x. So you can see here the 1 divided by 1 plus e to the power of minus x. So this is really the representation. You can actually take either or, but this here is what we actually saw earlier. Beta 0 is the intercept term, and beta 1 is the coefficient for x1. And y hat is really the predicted output with the real value between 0 and 1. Now to convert this to a binary output of 0 or 1, we can basically have it rounded to an integer value or set a cutoff point. Now what do I mean by cutoff point? So let's just say we have a range of figures. I'm just going to use an array. So let's just say 0, 0 0.4, 0 0.6, and 0 0.8, and 1.0. So let's just call this temporary. Okay, so if we print temporary out, this is what it looks like. So if I say round, I should really use numpy, don't I? Round that, you can see that the actual value get rounded up to, for those that's above 0.5, it get rounded to 1. Those that's below 0.5, it get rounded to 0. So this is what you get in terms of the binary value, meaning either 0 or 1. Okay, either or. So far, what we've learned about in this segment really is the sigmoid function, where to get resources to learn and understand about logistic regression, and the actual behavior of the sigmoid function, or very similarly the logistic regression, and finally the actual logistic regression equation itself, and how do you actually convert this predicted value here, the y hat, to become a binary value, because as it is right now, it looks more like probability, anything between 0 and 1. And what we want to do is that we can actually convert it to a binary value. So let me just I accidentally delete that. Now, what if you don't want 0.5 to be your cutoff point? Can you actually move that around? The straightforward answer is that you can, and this is how you typically do it. You say, okay, I want any value that is below 0.7 to be 0. Anything above that to be a 1. So okay, so you have to convert it to a numpy array and have this notation here. Is it greater than 0.7? And what you get here is false, 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 which is 0, and true, true, which is 1. So you can actually set your so-called cutoff line as you like to determine which point is 0, which point is 1, or which point where the actual demarcation of true or false and 0 and 1 is. Now, before we go on to the next portion of applying logistic regression and fitting and running prediction, as well as fitting it into an actual data, I'd like you to actually try an exercise before we leave, just to cement your understanding of how logistic regression goes. So just to revise, what we've covered is the basis of logistic regression. It is used predominantly for two-class problem. It is quite frequently used in the marketplace, either for default prediction or for the purpose of fraud detection. And this is really the shape of what a sigmoid function is and how it relates to the logistic regression. We've also actually explained that. And this is really the shape or the actual formula that describe how logistic regression looks like. So the exercise now really is asking you to actually try changing the so-called default level. Okay, whether it is a true or false, what is the actual cutoff point, which segregate the so-called classification. I'd like you to try a couple of variations of numbers. Notice that we actually have 5 data here, as we've explained before, 0, 0.4. What happened when you actually try 0.5? And what happened if you try 0.3? Do you get a different so-called outcome here? I'd like you to pause the video, play around with this, tinker it to see if it actually really matches your own intuition. Pause the video now, and when you come back, I'll summarize and explain what we're going to cover in the next video. Now, how did that go? I hope it went well, and you've developed further intuition of where the actual cutoff point that you set has a direct consequence to the actual classification result itself. When we come back in the next video, we're going to run some predictions with logistic regression and using a data set, a fictitious data set, and also trying to learn the logistic regression model using either stochastic or maximum likelihood. We're just going to touch on those and how to make use of scikit-learn to estimate the coefficient so that we can actually have a model to run prediction. So when we come back, this is what we're going to cover. I look forward to seeing you in the next video. Thank you.